So we've just explored the systematic review by Ramani and Sharifi, which established the LCZ framework as the diagnostic tool for reading urban heat landscapes. Now I want to show you how we're testing this framework in practice, specifically in Johannesburg, South Africa. This represents a pilot investigation, a reverse urban heat island analysis for the Greater Johannesburg metropolitan region. We're using peak summer data from January 15th to February 14th, 2025, sourced from ERA5 Land Climate Reanalysis. The title gives away the surprising finding, Johannesburg's cool heart, but before we jump to conclusions, remember, this is a preliminary exploration with 1 month of summer data. What we're really testing here is whether the LCZ framework can generate actionable insights for African cities where this approach has been underutilized. The findings themselves are tentative and may look completely different during Johannesburg's cold, dry winter season. Let me walk you through how this analysis was done. It's a powerful combination of human expertise and machine learning. For the LCZ classification, we used the global LCZ map created through the WUDAPT initiative. This combines two inputs: human digitized training areas from Google Earth, experts identifying this is definitely compact high-rise, this is definitely scattered trees, and Landsat 8 spectral data showing what the satellite actually sees. A random forest machine learning algorithm learns from these examples and classifies the entire city. Think of it as teaching a computer to recognize urban forms the way a human expert would. For the climate data, we used ERA5 Land Reanalysis from the European Center for Medium-Range Weather Forecasts. This combines millions of weather observations with atmospheric physics models to give us hourly temperature at every point on Earth. We sampled 10 locations across Johannesburg's urban-to-rural gradient. Here's what made this analysis feasible: Google Earth Engine. We extracted 7,200 temperature observations, 30 days, 24 hours per day, 10 locations, in just 46 seconds using the Python API. Without cloud computing, downloading and processing this much satellite data would take hours or days. Earth Engine brings satellite data analysis from the research lab to the classroom. All statistical analysis was done in R using the LCZ4R package, specifically designed for local climate zone research. This open source approach means anyone can replicate our findings. Now let's zoom into central Johannesburg to see the urban mosaic revealed by our LCZ classification. The CBD appears as that dark red, compact high-rise zone in the center, the iconic downtown skyscrapers that define Johannesburg's skyline. Just to the north, Sandton presents another compact high-rise and mid-rise cluster, functioning as a second CBD with its modern office towers. Between them, Rosebank emerges as a transitional zone, mixing compact and open mid-rise development. To the west, Soweto displays a distinct mosaic of compact and open low-rise residential areas, a morphological signature reflecting decades of urban development history. What's critical for our thermal analysis is observing how these vegetated zones, shown in green, penetrate throughout the built-up areas. This spatial distribution of green fingers helps us understand the potential cooling corridors and thermal refuge zones within Johannesburg's urban fabric. The LCZ framework allows us to connect these morphological patterns to their thermal behavior. This side-by-side comparison perfectly illustrates the morphological contrasts we're investigating in Johannesburg. On the left, the CBD and Sandton represent the economic engines: compact high-rise, LCZ1, and mid-rise, LCZ2 zones dominated by dense built form with minimal green space. On the right, Soweto, home to over 1.3 million residents, shows a dramatically different LCZ composition. Here we see open, low-rise residential development, LCZ6, the characteristic township housing pattern. But notice the crucial detail. Even within this high-density residential area, green patches and scattered trees are distributed throughout. This vegetation, though modest, plays a significant role in the local thermal environment. Key neighborhoods visible include Orlando, with its iconic Orlando Towers, Deep Kloof in the center, and Meadowlands to the north. That large structure is FNB Stadium, the 2010 World Cup venue. What's important for our investigation? Soweto's predominantly open low-rise LCZ types, with scattered vegetation, contribute to more moderate temperatures, contrasting sharply with the compact built zones in the CBD. This morphological difference translates directly into thermal equity implications for Johannesburg's residents. This chart quantifies what we observed visually in Johannesburg's LCZ distribution, and the results are striking. The dominant zones are low plants, LCZ-D, and dense trees, LCZ-A, together accounting for over 50% of the metropolitan region's surface area. This is remarkable. Johannesburg is a major African city where more than half the land is vegetated natural cover. Now looking at the built environment types, open low-rise LCZ6 at 44.1% represents the largest built category. This is predominantly Soweto, and similar township areas we just examined. Dense and compact low-rise zones add another 26%, showing the prevalence of low-rise residential development across Johannesburg. Here's the critical finding. Notice that compact high-rise, the iconic skyline image of Johannesburg's CBD, covers a tiny percentage despite being the city's most recognizable feature. This LCZ composition is essential for interpreting our temperature results. The majority of Johannesburg consists of vegetation and low-rise development, with limited compact built zones. Understanding this baseline helps us identify where thermal inequities emerge and why certain neighborhoods experience such different heat exposures. Now for the critical thermal data from our Johannesburg investigation. This graph reveals a surprising finding that challenges conventional urban heat island expectations. The diurnal temperature patterns show all location types, peri-urban, rural, suburban, and urban core, following remarkably similar cycles throughout the day. Everyone experiences the morning minimum around 6 a.m. at 15 to 16 degrees C, then peaks around 2 to 3 p.m. at 25-28 degrees C. Here's the unexpected finding. Notice how tightly grouped these lines are. They're nearly parallel. The urban-rural temperature difference is only 1.2 degrees Celsius on average, which is much smaller than the typical urban heat island effects reported in other cities. The standard UHI is around 7 degrees. This is our first hint that something unusual is happening in Johannesburg's thermal landscape. Rather than seeing the expected strong urban heat island with significantly elevated temperatures in the CBD, we're observing a minimal gradient across the metropolitan region. This finding sets up the critical question: if Johannesburg doesn't follow the typical urban heat island pattern, what thermal dynamics are actually at play? This is where our reverse urban heat island analysis becomes essential.